we have still 1 point from this 4th week, which is now, and then we can proceed to the 5th week. So the point which is still there is derived homomorphism, because we already finished 1-parameter groups and exponential mappings. Perhaps you remember. So derived homomorphism. Start with it is homomorphism derived with with respect to another homomorphism, and this is homomorphism of 2 Lie groups. So let's start with the fact that we have a homomorphism from Lie group G to Lie group H. It's here. Here is the picture. Now, we already know that on each Lie groups, or every Lie group, we have a lot of 1-parameter subgroups, infinite number. Say G, yes, GT. And now this 1-parameter subgroup is a curve. It can be mapped by this mapping F to the group H. Yes? So, because it is a homomorphism, we call that homomorphism of groups preserves multiplication. So this is our input. And also it preserves unit element and inverse, which we do not need now, yes? The complete structure. So because of preservation of this unit element, we also, when we map by F the starting point, it is the starting point which is again unit matrix in this other group, which may be unit matrix of different dimension. And here, let this be F image of this GT. And we can call it HT because it is on the group H. And it has one interesting property that, namely, what is HT plus S? By definition, it is F of G, T plus S, but G was 1-parameter subgroup. By assumption, yes? So, it has the property that this is G, T multiplied by GS. Now, homomorphism sees product. It acts by this property. So it is F of GT, F of GS. And this is nothing but H, T and HS. So this is the property of the curve here, which is a mapping of a very special curve, 1-parameter subgroup. And what we see, that what is this HT curve from this property? Yes, it is a 1-parameter subgroup in the group H. One parameter subgroup in H. So whenever you map one parameter subgroup in G, you obtain one parameter subgroup in H. But how this one parameter subgroup in G looks like? We came to conclusion that it is exponential of T sum C, and this C is from Lie algebra of the group. That all one parameter subgroups are of this form. But this means then that HT is also E T sum C tilde, which is now from the Lie algebra of the second group. So for each one parameter group, you have a unique element in the Lie algebra which generates this group. It is the initial velocity. So here we have some C, and here we have some C tilde. And of course this C tilde comes from this and this. Yes, it depends on what was originally C and what was the mapping, nothing more. Yes, so we will denote it as F primed C, which means that it depends on C, it depends on F, but it is not F of C because it doesn't make sense here. So it is some derived F. This is definition of the C tilde, or this is definition of this mapping. That whenever you have homomorphism of Lie groups, you have some mapping F primed, which is a mapping of corresponding Lie algebras. We can write a diagram that here will be this mapping. Here I will draw Lie algebra of G, and this is the mapping, that exponential mapping. We know that exponential mapping goes from Lie algebra to its own group, Lie group. Here is also Lie algebra and exponential mapping. It is another exponential mapping, but of the same structure, that for each G you have exponential mapping from Lie algebra to Lie group. Yes? So technically it can look different, this, but it is still G. In more pedantic way, I should write here exponent xg and xh, but we know what does it mean. And now what happens? That we discovered some mapping also on this level, which is called F primed. And the formula of which defines this Fs prime is that if you act by F on E T C, you obtain E to T F primed C. So this is the definition of this mapping. Yes. It came from this computation, that such mapping should exist there. Now, for t equal 1, in this definition equation, what we see that we start from C, then go to E to C. Yes, so from C we go to E to C, is here, and then in the second step, this is by exponential map, and this is by the map F. We go to F of EC, already without this T, because it is T equal 1. Yes. And here, what we see here, first, we go from the same C by F primed to f prime c, and then by another exponential, sorry, here, to e to f prime c. And this equal sign tells us that you get the same thing, that this thing is this thing. So what does it mean on this diagram? That composition of these two arrows gives you the same result like composition of these two arrows. This is something frequently used in mathematics, and it is an example of a commutative diagram. So there are many commutative diagrams. Here is one of them. And it is quite useful because it tells you something, yes, that if you draw this picture and tell me that this is a commutative diagram, I know something from it. I know that these two mappings give you the same thing like these two mappings, so actually I will obtain this equation for t equal 1. And it can be used with different logics. Here it is used that this formula defines this mapping, and this mapping closes the diagram. So after writing this mapping, we obtain commutative diagram. Yes? Now we would like to have some algorithm for computation of this. So we see that it is here. What is this exponential? Because we are speaking of matrix Lie groups, we already know, we saw several examples how it was computed. It is exponential of matrices. It is the series which is exponential of numbers when numbers are replaced by matrices. So this is also some series. First term is 1, second t, and this, and so on, this matrix, and so on. So we would like to compute it, and we see that if you write down this series, the first term is without t, the second term is linear in t, and so on. So if you do d over dt in 0, what you get is exactly this. Yes? So this is d over dt in 0 of the whole thing, clearly, because of the structure of the series. But then it means that it should be also d over dt in 0 from this left-hand side, if it is an equation. So we can write that f primed c equals d over dt in 0 of the left-hand side. And, well, this is good definition in the sense that it defines f primed in terms of f. On the left-hand side is the thing which I want to compute. Here is something which I know, and algorithm how to compute what I do not know. But there is even maybe more practical way how to do it, namely make the beginning of the series, so put t equal epsilon and use that e to epsilon c is 1 plus epsilon c, plus to the order of epsilon, it is whole story, yes? Then we get that f of 1 plus epsilon c is here. If we have epsilon here, it will be 1 plus epsilon this guy, plus higher terms. Of course, plus something and plus something. So this is very useful formula. equivalent to this one. It says the same thing actually, but this is maybe simpler for direct computing of what it defines this mapping, this formula. So how do we compute this mapping? We know the formula for f, otherwise we cannot do it. We cannot compute f primed without knowing f. So we know f on any argument. So we compute from this formula on any argument that what f actually does on this kind of argument. It is not just one argument, it is infinity of possibilities for differences, but the argument of this structure. You always get 1 plus epsilon something. Then read the something after epsilon, and this is the whole story. Yes? We will see it on some example, maybe on even 2 examples. And by the way, this commutative diagram is extremely important. It will be applied in many situations here. Maybe we will be even confused that now we use this commutative diagram for this situation, now for this situation, and so on. And in several distinct situations, we obtain interesting results. Yes, so this is worth remembering, this commutative diagram, this picture, because it will be used a lot of times already today. So we just now want to compute it for some example that I will write down some homomorphism of Lie groups, and we will compute the derived homomorphism. Before I want to say something which I forgot, very important, that up to now we do not know any property of this mapping, but it has very important property. So it is called derived homomorphism. So it is this f primed, which is called derived homomorphism. The original homomorphism is f, and the derived homomorphism is f primed. So first, it can be defined in other way, using other way of working with Lie groups, namely with differential geometry, and it can be defined through something which is called push-forward mapping, which we will learn on this semester, maybe in something like 3 weeks. And then the properties of this guy is completely clear. Without this, using just matrix manipulations, one property is quite simple, and the other important property is not that simple. It is not hard. It is quite simple. It needs some 5 minutes of computation, and you can prove it. But I will not do it because we need just to know it, and I don't want to go to more complicated computations in this language because it is better to do them in better language. So after we learn differential geometry, which is maybe enough for it, next year on Mathematical Physics 2, we will speak about the application of the other language to this same situation. So I don't want to go to do more complicated computations in this matrix formulation. It is cumbersome because there is a better formalism for it. But now I just mentioned what are the properties. The properties is that this is a homomorphism, like is in the title, but of Lie algebras. So what is homomorphism in general? It is mapping between some two guys of the same type, that homomorphism of Lie algebras is mapping from one Lie algebra to other Lie algebra. Homomorphism of two groups is mapping from one group to other group. And what does it mean that we call it homomorphism in general? For what holds for each kind of structure? By definition, that when we speak of homomorphism, preserves the structure, exactly, yes? So now we should ask, what does it mean that it preserves the structure of Lie algebra? What kind of equation should we write? That there are just two properties, and what are the properties? What does it mean, preservation of structure of Lie algebra? So what is the structure of Lie algebra? Sorry? Yeah, including, but first, what are skew symmetry is of what? What has the skew symmetry in Lie algebra? Sorry? The bracket, yes. Lie bracket or commutator, it is the same thing, should be preserved, yes. So this applied on x, y should be f x f or prime, sorry, primed y commutator. And remember that this is the commutator in G and this is the commutator in H. So they could be completely different. So this is the second property. And the first, the simpler one, is what? Preserving of what? What is even before this commutator in the definition of Lie algebra? Linearity. It is a linear space. So here should be x plus lambda y should be f primed x plus lambda f primed y. Oh, sorry. 2. So it turns out, as is usually the way how to tell it, it turns out that this mapping has these nice properties. So, of course, this mapping also has some nice properties. They are just homomorphism. So, if this is homomorphism, this is also homomorphism. But this is homomorphism of Lie groups, and this is homomorphism of Lie algebras. It is something completely different. And it is always the case. So, it is a canonical construction that from homomorphism of some structure, you can derive homomorphism of another structure free of charge. So now I will show one example. Perhaps I didn't forget something important. Well, if I do, I will add it. So an example. So imagine this group and this group, and we will study homomorphism, which we'll call that because it is that, it is determinant. Yes. So the first question, really it is a homomorphism of this group, determinant. Is it true? So can you tell me a few words commenting what I have written that yes, it is a homomorphism?
The determinant of a unit matrix is 1.
Yes.
The determinant of the product is the product.
Exactly. So the basic property is the determinant of product of two matrices is product of determinants. And of course, determinant ends in numbers. Here are numbers. Determinant can be computed also outside this group for matrices which have zero determinant, so non-invertible. But here we restrict the determinant to invertible matrices. Then, more or less by definition, the result is in non-zero numbers, and it is exactly what is said here. Yes? So this we know from the first year of linear algebra, that in some complicated words we can, or conversely, in a simple words, we can say that this is a homomorphism. So we have a first line of this commutative diagram. Everything which is different from the first line is then automatic. So here is Lie algebra, which we know. Here, the same story. Here are exponential mappings. And here is something which we do not know, maybe, namely derived mapping to original mapping, which is determinant. And I write that I don't know what is it. But I see the properties. What is this Lie algebra? What are elements of this Lie algebra? Of this and this. Just to discover that what we are mapping, what to what we are mapping by this mapping. I don't know what is the mapping, I will compute it, but now just, it is a mapping from what to what? Yes, but all matrices, yes, here, to all numbers. Yes, because it is one by one matrix, maybe also degenerate. So, and if it is true, what is written here, it is a linear mapping. So it is a linear mapping, matrix goes to a number, some number computed from the matrix. Well, there are many possibilities. For example, here you have a number, a matrix, choose this element and put it here. This is some mapping which is probably linear, yes? That take any component and this will be the result of the mapping. But it doesn't look very, very nice, yes, this mapping. So there are several mappings, matrices to numbers. For example, determinant itself. But the determinant is not linear, so probably it will be not determinant. That this is some different mapping. Do you know some mapping which is linear on matrices and it is not, well, it is not determinant because this is not linear, but how to compute some interesting number from a square matrix and the number linearly depends on the matrix. We know one. So what? The trace. There is a trace. So maybe it is a trace, but it's just a hint. So we will compute it. I will use this formula to show that it is a good way. Well, try to think this original formula that, well, at least it is more complicated. It can be, of course, computed, but from here it is simpler. That here should be unit element in the Lie algebra H. Here will be number one, unit matrix in the second group. Unit matrix in the second group is number one. Yes, here. Plus epsilon and this mysterious mapping acting on C. The question is, what is here? This is our question. And we can answer this question doing some computation that what is determinant of this matrix. So, we already heard several times that it is a trace, really, yes? So I will write it, that it is 1 plus epsilon trace of C. That means that we already see the result, that it is really the trace. And just, I will tell the argument which can be applied for really n by n matrix, because it can be easily verified if you write down 2 by 2 matrix, trivial, 3 by 3 matrix, okay, I see it, but what about n by n? This matrix, 1 plus epsilon C, is 1 plus epsilon C11, epsilon C12, epsilon C 1n, here epsilon c to 1, there is 1 plus epsilon c to 2, epsilon c 2n, and so on. Here c n1 and 1 plus epsilon c nn, and we want to compute determinant from this. So just I remember you that determinant, one of definitions how to compute it is first choose any element, like for example this one. Then put away this column and this line and choose another element, for example this one. Then put away this line and this column and choose another, and so on. And when you have n pieces, multiply them and put some plus or minus and repeat the story for all possibilities. This is the determinant. Yes? And now, my statement is that whenever, the first possibility is to choose this, just product on the diagonal. And then some other possibility needs to choose something outside the diagonal, which, as we see, has always epsilon. And recall that we want to find what is near epsilon on this result, so not higher than just epsilon to the first power. Yes? And the claim is, if you start with some element which is outside the diagonal, then you have at least one element more, which is also not at the diagonal. So altogether, we have already epsilon squared, at least, maybe more. Yes? So the claim is that if you want to find epsilon term of this, you should just take only elements on the diagonal, no other elements. Because I repeat, if you start with any other element, you are forced to use also other element again, other than on the diagonal. And you have already epsilon squared, which you are not interested. So think it over, that by this method, whenever you start here, you have no possibility to have epsilon term, only epsilon squared or higher. So if you take the pieces on the diagonal and multiply them, this is the only guy who survives to the epsilon accuracy. Yes, 1 plus epsilon c to 2, and so on. So the first term is 1. Then is term epsilon, and it is obtained epsilon from one bracket and ones from other brackets. And so it is C11 here, here C22, CNN, and so on. And this is just trace. And higher. Yes. So by this way, you can see that really trace works for any dimensional matrix as an epsilon term of this series. So what we found, that determinant has a derived mapping, which is just trace. So how this formula, the fact that this diagram commutes looks like, that start with some c here, make exponential and compute determinant, and you obtain the same thing like if you start by c, apply trace to this c, and put it as an exponent. So we have this formula which is useful. You will see the formula somewhere in your study of theoretical physics, by sure. often it is proved. Did you meet it? Did you meet it? This formula already in some situation of physics or something like that? Because I remember that when I met it, the proof were usually by diagonalization of this C. If you diagonalize by some A and n minus 1, it is simple statement. But the problem is that not all matrices can be diagonalized. So you see that by this method, you have this formula without necessity to diagonalize it, to do it directly. Well, we will see the next applications. So we used already this diagram for concrete F, namely determinant, and it has some hopefully interesting result that trace is determinant primed. And now we go already to the next week, but in the stuff which will be next week, so from now, also today, we'll meet this once more times, yes? So it is not completely departure of these topics. It is more or less specification that now, from now on, we will speak of something which is more narrow, and we will have repeating of this stuff in a lot of cases. And this stuff on which we now restrict is very important, and it is called representations of groups, mainly Lie groups, but in principle other also, and Lie algebras. So this is the new word, that not the Lie groups or groups and Lie algebras themselves, but their representations. I write first the definition, and they will try to do it in plain English, what is there. So representation is a homomorphism between these two groups. This is some arbitrary group, and this is rather specific group, which we already know. Yes? We already mentioned it when we defined standard Lie groups. So they are invertible, some A, V to V, such that A to mine exists, and they are linear, of course. And we know that such mappings form a group, and it is called GLV. So the difference between these, I already told, is that this is the defining notation, that what we want, and this is the answer, so to speak. Do you want automorphisms of linear space? Think it over, and you come to the conclusion that they are linear mappings which have invertible elements. Yes, because it preserves everything you need. And automorphisms here are mapping V to V, but preserving structure. So linear and so on. So this is the definition, that this is a representation of this group in this vector space. Definition is also, if this vector space has some dimension small m, then this is called also the dimension of the representation. So three-dimensional representation means that this V is three-dimensional vector space. And this vector space may be, by the way, real and complex, for example, then the representation is called real representation or complex representation. Now, what it means actually, do not forget that I used the word that this rho is a homomorphism. So it means that if in your G you make a product, so we have altogether 3 elements, G1, G2, and this product. Then, if you compute what are these elements? Once more, these are linear operators, also the correct word. Yes, linear operators invertible. So here you have 3 linear operators. This is one of them. Here is another one. And here is the third one. So as soon as you have a fact that you have 2 elements and the third one their product, after homomorphism, you will have, instead of this, some linear operator, instead of this, another linear operator, namely this and this. And now, the important thing, that linear operator, which is associated with this group element, is already given. It is the product of the 2 operators. What is the product of the operators? How the product in this group is defined? Composition, exactly, yes. So this is the composition of operators that first acts this operator, second this operator. Now, first example. Whenever we speak of matrix groups, so examples, yes. First, if G is a matrix group, so its element is a matrix. And I can misuse this fact that it is a matrix, that I will regard it as an operator directly, that each matrix is an operator. On what? On some columns. Yes? So whenever I have a square matrix, I can interpret it that this is an operator of a column correspondingly big. Yes? That if it is n by n matrix, the column should be n by 1. Otherwise, it is not right mapping. Yeah? So we have a mapping, x1, xn goes to this. And here the matrix serves as an operator. So I can define such funny representation that the homomorphism here, what is here? It is strange thing. This A should be as element of the Lie group. And this should be treated as a matrix. So the operator. Element of GL Rn or Cn, if it is complex. So we leave the matrix as it is, but we just reframe our point of view that here it is as a group element and here it is as an operator, because it is naturally an operator. This cannot be done if your group is something else than matrix groups. But because we restrict in this semester to matrix groups, this is the perfect way to do it. That we already have a nice formula for a representation that leave the matrix as it is. And now the question is it a homomorphism? It's a very hard question. Does this mapping preserve multiplication? Well, it is strange to believe that it does not if it is the same thing, yes? So, of course, it preserves everything because it is identity mapping, yes? Second thing, that define row A as a unit operator in any vector space. For any input element of G, this is now some element of G, and you assign unit operator somewhere. You specify any V, for example, take R1, the simplest possibility, but it is not needed. But if you have no idea to find some V, take just a real axis. It is a nice vector space. And what is unit operator in this vector space? Number 1. So in this case, in the bracket, this is just put number 1 to any input element of the group. Now the question is it a homomorphism? Check that it is. It is also trivial. Yes. So this is another possibility to define a representation of any group if you have no better idea. Sometimes it is very important to do it in this way, but now I speak that we want to see several examples. So let's start with the first example, that just leave the matrix as it is. First, more or less trivial example, also very important, but technically trivial. And second, also important, technically trivial example that put everything to 1. It works. And the third one is repeat the story with the homomorphism. That take rho of A equal determinant of A. So, in which vector space now we have, what is this V? If it is representation, in which V? R. Why? We have the result of determinant is a number, either real or complex number. Now, the number should be operator somewhere, so it is actually this case, yes? So it can be treated now as a representation, but only in one-dimensional vector space, yes, because the operator is one-dimensional. And it should be just treated, is it really here? So it is, by this formula given on the right-hand side, a linear operator. It is a number. So a number is a linear operator if the number linear space. Yes? So it works. It is also a representation. It is one-dimensional representation, either real, if you have real matrices, or complex, one-dimensional complex, if you have complex matrices. Now, well, the fourth, it is actually a particular case of something more general, but do it explicitly, that rho of A at B is A, B, A to this, A to minus 1. So just if we want to make sense of this formula, what should be B? A is some matrix, element of some matrix Lie group, say SON or something like that. So what should be B in order that this formula should make sense? First of all, it should be some element of some linear space, because representation has the property that A is element of group, rho A is already an operator somewhere. So this guy is from this somewhere. It should be some element from some linear space. And from here, in order that this makes sense, we see that B should be what? What linear space is there? Yes, matrices. So this B is matrix of the same height and width as this A. Yes? So it is rho of this matrix applied on this matrix is multiply three matrices. Here is B, A to minus 1. First of all, is it a linear mapping? So imagine here B1 plus lambda B2. It will be here, then multiply, and you see very easily that yes, it is a linear mapping. So it is a representation of G in linear space of matrices n by n, such like G, which is something like R to n squared, we know. By checking B1 plus lambda B2, we see that it is linear. So it is a really linear operator. What should be checked? The next thing or the last thing? We already know that, yes, there is some nice vector space. The operator is linear, but still we don't know whether the last step holds. What is the last step? That it is a homomorphism, yes? So we should check that row of A1, A2, whether is row of A1, row of A2. We don't know. So apply both sides on B. That what should we check? What is this by definition here? It is A1, A2 multiplied by B, and here A1, A2 to minus 1. What is here? It is A2B, A2 to minus 1. And what is this? It is A1 applied to A2B, A2 minus 1, A1 minus 1. Now, is it the same or not? Here, A1, A2, also A1, A2. It is, the brackets are not important. Yes, it is associative. So here is A1, A2 to minus 1. Here is A2 minus A1 minus 1. It is exactly this term, yes? So we checked that it is really a homomorphism. So we have n squared dimensional representation of some n-dimensional matrix group, of any n-dimensional matrices, n by n matrices, I mean. Should act if it should make sense. Okay, now we can turn this. We already know basics of what is a representation of the group. And now we remember that by definition, it is a homomorphism of two groups. But we know that whenever we have homomorphism of two groups, we can apply this diagram, which is there. So we will write the rest of the diagram. Here it is some G. Here it is something. We think over. Here is exponential, and here should be row primed. First, we will think a little bit what is here. That what is Lie algebra of automorphisms of V, that is GLV. It is something small GLV, yes, by just notation. But what kind of Lie algebra is? What elements live there, and what is the way how they are commuting? So we know that this group has, when we insert a basis to V, yes, EA in V, we know that there is a bijection of A with matrices. So this group is isomorphic to the group of non-singular matrices, because this group has also inverse element to any isomorphism actually of V, and this also should react somehow. Yes, that these matrices should be with determinant non-zero. Now Lie algebra is found in such a way that put this ansatz and find all C's which obey the properties which are needed from A. Here, the property at the matrix level are that determinant of this matrix cannot be 0. Yes, but we already think over this. That what does it mean for C? That if this is from G, L, and R. So here is something from small g, L, and R. And how are restricted those matrices? Only in such a way that the determinant of this matrix should be not equal to 0. Yes? But determinant of this matrix never is 0 for epsilon. So there are no restrictions. G, L, and R are all matrices. Now, all matrices produce all linear transformations. So what is here? This is Lie algebra of all linear transformations V to V. All, not just invertible. Yes? All V to V. And they have a special name, endomorphisms of V. Endomorphism means morphism to the same space, so to speak, to the same set. So morphisms of V are linear mappings. Endomorphisms V to V, linear mappings V to V, all of them. So the difference with this, not all of them, just invertible. Here, any is good. So I will write officially the Lie algebra is all linear mappings V to V. What is the commutator? It is commutator of the structure CD minus DC. Think it over, yes? Because this is at the same time associative algebra, that linear mappings from V to V can be multiplied in the sense that composed. And by this construction, you create a Lie algebra from associative algebra. So we already know this diagram, it is this general diagram applied to any representation, any representation. So now what is the definition of this guy? Just like in general case, compute this arrow on elements 1 plus epsilon C, and you by sure obtain unit operator plus epsilon, by definition rho primed C. And this is definition, by this equation we define this operator. Yes? And we know from the general scheme, we know that 1 and 2 property holds. So it has property that rho primed C plus lambda C tilde is rho primed C plus lambda rho primes C tilde. And second, that it preserves commutator rho primed C commuted with rho primed C tilde. But now the commutator is already specified in this way. So this is the same thing like rho primed C tilde minus rho primed C tilde rho primed C. So this is a little bit in more detail that what is a commutator. Yes, in general, the commutator can be various things. Yes, this commutator here, but it can be complicated. For example, this Poisson bracket or something like that, or vector product. Yes, we know that there are some strange commutators, but here it is this most famous commutator, AB minus BA, in representations. So let's compute it. How is it called? This is called derived representation. In general, the mapping is called general derived homomorphism, and of course it is homomorphism and derived, but because our homomorphism of groups is called representation, it is called derived representation. And what does it mean this? Now it is, by definition, it is representation of G. So what is a representation of Lie algebra? Representation of Lie algebra is assigning to any element of Lie algebra operator in some vector space, as we see. And this assignment has these two properties. That if you assign to C, rho prime C, to C tilde, rho prime C tilde, then necessarily to this element you have assigned this operator, and also to commutator. You have no choice already. So in few words, it is a homomorphism of Lie algebras. But homomorphism from given algebra, which is to be represented, to very concrete Lie algebra of linear operators somewhere. This is representation of Lie algebra. So it is very similar, like representation of group. What is representation of group? That's assigned with any abstract group element linear operator, but in order that it should be a homomorphism, this linear operator should be always invertible. But here it cannot be not invertible. It can be also not non-invertible because we don't need it. Yes? For our homomorphism, we do not need invertibility of these operators. So it is a difference between representation of group and representation of Lie algebras. Have a look what is next. And let's compute, just to see that how it works. We already checked that this is a representation of group. Any matrix group on the linear space of square matrices of the same dimension. Yes, like the dimension of the group. Now notice, this is a general rule, that whenever you compute derived representation, you obtain operators in the same vector space, like was the original representation of group. Yes. So our operators, we want now to compute rho primed C, and we know already that it will be a representing operator acting on the same B's like the group elements. Yes. So the question is, what is this? How it works there? So we can compute it directly from here. By definition, we should apply this on elements very near to unit group. So 1 plus epsilon C, apply on B. From this formula, what it gives? 1 plus epsilon C multiplied by B, and what is the inverse element to this one? It should be something which, when you multiply it with this, will give you unit matrix to the order epsilon. If A is 1 plus epsilon C, this is very near to unity. The A to minus 1 should be also very near to unity. Think it over. It cannot be far from unit element if the original element is there. So it should be something like 1 plus epsilon some tilde, I don't know what. And now their product should be 1. This is the definition of 2 minus 1. Now with accuracy to epsilon. So if you multiply this, what do you gain? 1, it is from this. 2 guys near epsilon, namely this and this, and this and this, it is C plus C tilde plus epsilon squared something. So if it should be 1, and it is this and should be 1. So we see that this is to be 0, so here is 1 minus epsilon C. This is the inverse element. Now, do a multiplication with epsilon accuracy, and you obtain that it is B from 2 ones, and epsilon CB from this, and minus BC from the second, and plus. And here it should be 1, or sorry, this should be 1 plus epsilon rho primed C acting on B. 1 acting on B gives you this B. So this guy, which I am interested in, acting on B, gives, without epsilon, this. So the result is CB, commutator. Now we can check. This is the result of our computations, and if the computation is okay, we believe that this is a good result. But imagine that some friend of you comes to you and tells you that I discovered interesting representation of Lie algebra, namely by this formula. Yes? And you don't know the history. You cannot go to the computation because you have just the result. But you can check whether the result works or not. What should you check? Is it a linear operator first? Check that it is. Does it preserve, it is linearity in this B, whether it is linear operator. Okay? Now, this linearity is linearity with respect to C, plus commutator, that whether rho primed of commutator C tilde is the same thing like rho primed C rho primed C tilde minus rho primed C tilde rho primed C. And this, whether this is true, acting on B. Yes? So this linearity with respect to B and linearity with respect to C, which is completely different on the left-hand side, here it is just linearity of the commutator with these 2 inputs, which we know that it is true. Yes? This commutator is bilinear. And can you imagine some property of this commutator from which we can see that also this applied on B gives you this applied on B? Can you imagine some property of something which we know that when inserted, it will give you that yes, it is true? If you know that this formula is given by a commutator. So for example, what kind of expression is application of this to B? First, this applied to B is one commutator. Then this applied on the result is iterated commutator. It is commutator with this commutator. And there are 3 terms, first, second, third. Do you know something where are 3 guys iterated commutators? Jacobi identity, yes? So apply Jacobi identity and you will see that it is true. Yes? So we can check that this is working formula, that really it gives a representation of Lie algebra somewhere. We know also, of course, that where. On the matrices of the same size like C. It is not directly visible. You have to check it. Yes? Maybe some small things you will see, but for example, this preserving of commutator is a little bit non-trivial. You can, of course, think in advance that it should be connected to Jacobi identity, but there are some pluses, minuses, and so on, so maybe it doesn't work, but that's why you should check it. So we also can check it in spite of the fact that we derived it, because we maybe made some mistake in our derivation, that always it is a good idea if you compute something which should have some property, that check whether it really has some property, because if it is not the case, you have some mistake in your computation. Okay, what's the time? We have still almost 20 minutes. So it makes sense to start another line here, which has three concepts, namely conjugation, adjoint representation of G, and adjoint representation of Lie algebra G. And it is too much, maybe, for 19 minutes, but we will just start and then go on next week. So, three things: conjugation, then this representation and this representation. This is of Lie group, and this is of Lie algebra. And actually, this small ad is big ad primed. So it is derived representation to the second line. So first the conjugation. I will not now go to the interpretation of conjugation. It has very nice interpretation, that what it really means. But for us now, for us conjugation is now not the primary interesting thing. The primary interesting things are these two guys, and they can be somehow computed from this conjugation. This is one possibility. Another one is just define it, how it works, and you can check that it works. But the better way, I think, that is to derive them from the conjugation somehow. So because of that, I do not explain what conjugation means visually. It means something. And it is quite useful to know it, but not now. We will maybe treat it later on when we will study actions of groups somewhere, which is in the syllabus. So, just definition. Conjugation, I will, and also in many authors denote it like that, is a mapping from G to G. And it is given by an element from G. So there are so many conjugations, like you have elements of G. It is not just one conjugation, but for each element, you have a mapping from G to G, which works like that. That is, so to speak, sandwiching of this K by G from the left and K and G to -1 from the right. This is very important concept, for example, of studying finite dimensional representations. If you go to the lecture of quantum mechanics and so on, when you have things like that, you can see it. But now, just this is the definition. Important thing that here is a multiplication in the group. 3 elements from the group are multiplied, so it is well defined. Now it has a lot of nice properties in spite of the simplicity of the definition. For example, if you compute conjugation with respect to a product, This is a conjugation with respect to G. Now, what about the conjugation with respect to product of two G's? So it is G1, G2, bracket, K, G1, G2 to minus 1, but this is, as we know, G2 minus 1, G1 minus 1, and now this in the middle is conjugation of K by element G2, and then, so it is some element of group already, and now this element of the group is again conjugated by G1. This is on K. So without K, we have this property. Yes, so we see that the conjugation preserves the multiplication in this sense. Now, it also preserves the multiplication in another sense, that what about K1, K2? This G, K1, G to minus, K2, G to minus 1. But we can insert here unit element G to minus 1G in order to see that it is just IG applied on K1 multiplied by IG applied to K2. Of course, if you apply it on unit element, where it is here, if this is unit element, just G and G to minus 1 cancels. So we again obtain unit element, and you should check that inverse element goes to inverse element, yes? So what does it mean? That how can we name this conjugation, that it is what? Homomorphism of Lie group, yes? Not just necessarily Lie, homomorphism of group. But actually it is more than homomorphism, because we can check from this formula, for example, that it has an inverse, namely that it is conjugation with respect to inverse of G. Check. Yes. What is the consequence of this fact to our knowledge that this is a homomorphism? That we can say stronger statement. This says that it is a bijection, yes, because you have inverse. You have now bijection of group on itself, which preserves all the structure of the group. So it is not only homomorphism, but it is isomorphism. But because it is isomorphism, not on different group, but on the same group, it is called automorphism, yes. But for us now, it's quite enough that we can write such diagram like that and put this conjugation here simply as the first line. So the first line will be IG to G. Then everything else is automatic. This is the strength of this diagram. And here will be IG derived, yes, primed. Now, what is this mapping? It is a linear operator acting on the Lie algebra with a result in Lie algebra. So it is a linear operator in Lie algebra. But linear operator on Lie algebra as a linear space. Yes? Here we do not use at all the commutator, just the linearity property of this space. So it is a candidate to become a representation. Because have a look that you have a G here. For each G, you have this linear operator in some linear space. So probably it is some rho G. When it will be the case? If it preserves multiplication of G on this slot here. So if it is homomorphism. So the question is that this is whether this is the product that is composition and you can check this directly from this diagram that if you write it here for G1, but because it is from G to G, you can go further and do this with G2. And then you have some composition arrow, and the same will be here. And composition. Write the corresponding numbers, 1, 2, 1, 2, and so on. And you will see that this is true. Because it is true here in the first line. Because something is true in the first line, you will see that the needed property is true in the second line. So actually it is a representation. Yes? Because it is a representation, we will call it somewhere. Now, the representation is very specific. What is interesting? Usually, or typically, when we have representation, it is already away, but it is in some vector space. So if you want to find a representation of a group, except for the group, you will have this vector space. You need this material that I will when I want to construct a representation, first I have the necessity to find some vector space when the representation works, and then by the formula how it works in this vector space. But here, it is represented in the Lie algebra of the Lie group. So you have one vector space there, simply. Whenever you have Lie group, you have a vector space, namely the Lie algebra. So this is the interesting case that starting from any Lie group, everything else is already done, that conjugation works canonically. You have prepared vector space when possibly some representation happens. And from this diagram, we really see that, yes, there is a representation which works on the canonical vector space given to any Lie group, namely its own Lie algebra. And because of this fact, it is very important in the sense that you can see it in many places, in mathematics and in physics. In many places, this representation, which I will label in a moment, you can meet. For example, there is a famous place that you know that there is something like standard model of elementary particles, and you also perhaps know that it is an example, very successful example, of so-called gauge theories. There is something like gauge theories discovered sometimes, and this is one possible gauge theory for some group and some details. And in each gauge theory, this representation here plays an important role. I have this lecture, Gauge Fields and Connections, for you, that is in 1.5 years from now. And then it can be seen, if you are interested, that how this representation comes to any gauge theory, that these gauge fields are somehow transformed in terms of this representation. So, because it is so exceptional, this representation, it deserves its own name, that not just IG prime, this is something not very nice name for such important representation. So mathematicians invented that this will be denoted adjoint representation. This is the name. So it is some representation, raw, but very concrete. Notice the notation that usually when general representation is somehow displayed, the G is inside the bracket as an argument. Here is not add bracket G and so on, but it is written like an index. It is only for typographical reasons, that if for some formulas, computed for this representation, it will be very problematic to write it in this notation. It will be somehow misleading. So because of that, here the G is not in the bracket as it should be officially, but as an index. I just stress that it is the case. So in this diagram, we have this already very interesting thing, adjoint representation. So as we see, it is a representation in its own Lie algebra with all consequences. Yes, that it is a mapping for any G, it is a mapping from any G from group, it is a mapping from Lie algebra to Lie algebra, linear operator, which is homomorphism, that if you have here G1, G2, it becomes the product. Now, I think that we already had this diagram, yes. For any representation, here, automorphisms of any V, we had this line which is here, rho primed, with two exponentials. Do you remember that there was this diagram on the blackboard sometimes on this lecture? So we can now put this rho to be this adjoint, concrete representation. So it should be some derived representation to adjoint. What is the particular diagram? G goes to automorphisms of the Lie algebra. Yes, because our V now is the Lie algebra. Here is Lie algebra. Here is this adjoint primed to be computed. And here is endomorphism of Lie algebra. Because this adjoint is important representation, also its derived representation is important because they are friends. That means it deserves its separate name and it is called adjoint by small ad. So here I will already write just the official name, but it is derived representation to this particular representation. And we want to compute it. We will not do it already because it's not time for it. But what we want to do next time, how it works. So adjoint representation works in Lie algebra. Yes. So it should act on some element of Lie algebra, and the question is how. Now, this representation is representation of Lie algebra. So, represented element is here. Once again, from typographical reasons, it is as an index not in bracket, as it should be. And it should be from here. So, it should be an operator acting on element of Lie algebra, on some Y. The question is how it acts. Both these things will be computed next time, yes? But think it over that if there are some representations, we want to know the answer to this line and this line, that how it exactly works, and then we should check whether it is really representation of a Lie group, a representation of the algebra. Yes? So thank you.